Yeah, so I guess start with a brief bit about me. I've been a member of the ACCU since 2008 or so just kind of over 10 years. In fact, I met Phil whilst working at a certain investment bank that a considerable number of ACCU people seem to kind of work at. And it was whilst I was there that I discovered the ACCU and various people who have, kind of met up with since in kind of ACCU London. So yeah, my background is generally, I guess, kind of enterprise grade technology, if you want to kind of call it that, rather than sort of embedded or that kind of side of things. Generally, about 15 years or so of sort of C++, and then I kind of switched from that to C# and kind of more kind of web services type stuff for a while, and then more recently involved with a hedge fund who, surprisingly enough, are using D for all their stuff and writing their own language. So that's kind of a bit of fun, something a little bit different. But much of this talk has sort of kind of comes from apart from that sort of time earlier in my career, and then some of the examples that you'll see later are kind of more slightly kind of more recent. But so it's kind of more of a C# you feel the later one. There's maybe a bit of earlier kind of C++ you feel. Yeah. So test of strength. Those people who know me know that I like to play on words, and got to have a title for a talk. It's got to be a play on words, and this is kind of no exception really. So we're alluding to kind of two things here, I guess. One of them is a test of strength in the sense of kind of strength of character. What do I need to kind of, if you like, do the right thing to write tests and to consider what value they have and why I would write them. And then the kind of the second half of the talk. It looks at the tests in themselves in the sense of what does a strong test kind of look like? How do I write tests that aren't brittle, that kind of serve me well, and particularly kind of like for those people that kind of come after me. So it's been a kind of a game of two halves, and we'll kind of start off with the first part, which is a little bit kind of about me and my journey. There is an element, I guess, of a rite of passage here. I doubt that I can stop anybody from kind of going wrong, but maybe I'll at least allow you to short circuit your own journey by avoiding some of the mistakes that I guess I probably have made, or at least help you think about some things that help you decide what's valuable in the test and why to use it. Okay, so heading back to the beginning of my career, I started out in a small software house. We were writing graphics software. So the idea of at that time, there were no kind of unit tests as perhaps we kind of know them today, and being kind of very visually oriented, that wasn't sort of easy to have tested in any kind of automated way. So a lot of manual testing of features. We had a QA department. They kind of acted as the regression testers at the time. But essentially, the unit test in this sense tended to be kind of small manual tests. But a key part was that the products tended to be quite mature. We were adding kind of features, and therefore the things that we tended to test tended to be reasonably small and kind of like well focused. You could kind of like get most of the stuff that you were working on kind of in your head, and then the sort of more holistic approach was handled by another department. So it was kind of quite manageable from a kind of a manual perspective at that point. And whilst I was there in that kind of first job, I got introduced to a couple of books by a chap called Stephen Quire. He was, at the time, there were certainly some amusing jokes around the fact that somebody from Microsoft could have the gall to write about what it would mean to write solid code. Particularly at the time, we were working on Windows 3 and Microsoft Word, which certainly went through some flaky times. But there was some excellent stuff in his book, particularly introduced me to things like design by contract, and some other aspects around kind of testing and stuff, which we adopted at the company, and that made a kind of a considerable difference to quality, to sort of the internal kind of quality. And in particular, there was one particular, I suppose there was kind of two practices that particularly stuck with me, and that was the idea that whenever you've written some new code, you should step through it in the debugger. So you'd put a breakpoint on your function, and then you'd kind of walk through it, and you'd check your variables and stuff, loop preconditions and stuff, and so you could see whether it was behaving kind of as you intended. And there was sort of a nice knock-on effect from doing that, because to get something into the debugger quickly so that you could step over it, you essentially had to design a code and to design a way of getting to that point very quickly. It's no good if it takes you an hour to hit the first breakpoint, because it's not very productive. So you tended to kind of write code that was able to be tested by writing kind of custom test harnesses, that kind of thing. So there was a nice sort of knock-on effect on the design, but ultimately you were sort of using the debugger to inspect the state of it. I guess that particular approach lasted with me for sort of 5 or 6 years. It seemed to work out very well for myself. Certainly my bug count was notably less than many people around me, but I guess that was more by the people around me than specifically necessarily my practices. But hopefully, I'm hoping that those practices were sort of pay dividends. But unfortunately, it kind of all came to a head when I was working at a money broker's. And one day, a colleague of mine came over and mentioned that these some tests that he'd written for this licensing component we'd written had started failing. And I didn't really understand at the time kind of what he meant. So I said, kind of tell me more. And he mentioned that we had this little licensing component, and he'd been messing around with unit testing, and they had started failing. And given that we hadn't sort of touched the licensing component for some time, the candidate was likely to be, bug was likely to be maybe in the XML parser that we'd written, because, back then you wrote your own XML parser, not that you do that now. He was a very polite chap. He knew exactly what had gone on, because he'd looked in the source control, but he was being polite. And so we kind of looked at it together. And lo and behold, I discovered that as part of some refactoring work I'd done, I had missed out a call to a function that decoded entity references, your ampersand, amp, semicolon, at less LT, semicolon, that kind of thing. So despite kind of all my best efforts to kind of test manually and use the test harnesses and track things, somehow a little bug had slipped through, but this automated test had caught it, and that kind of made me realise that the practices that I'd been adopting for the last few years just weren't scalable, and we needed to do better. And this kind of automated testing thing actually sounded quite cool. So naturally, I asked him to tell me more about kind of what he'd done. And so this is an example of a test, a unit test, the kind of thing that he'd showed me. This is CPP unit, which was written by this chap called Michael Feathers, who didn't really sort of know at the time, but this was the kind of thing that we'd written. It was the first thing, I guess, that surprised me when I looked at it was kind of how verbose it was. My gut reaction was that I wasn't paid to write test code. I was paid to write production code. So surely, why would I be writing all of this code to write all of these tests? This didn't kind of appeal to me at all. What's interesting is that nobody in the organisation had ever suggested to me that I shouldn't adopt this approach of testing. I kind of, I guess, made that up myself, that I felt that whereas when you kind of test manually, nobody can really kind of see you doing it, and therefore, nobody can kind of challenge you, if you like. Whereas putting testing in code all of a sudden kind of makes that a very visible artifact, and kind of as a consequence, people kind of see how much time you spend testing, and that felt kind of somewhat uncomfortable. So I, naturally, being a programmer, we always like to kind of think that we can do better than the people who probably are smart. So I decided that I would see if I could do better. So I decided to write my own C++ test framework, something that I thought would probably help me write tests quicker. And what we have now on the screen is a test that I wrote for a command line parser. And this command line parser still kind of exists. The code is on my GitHub, should you decide to trawl back far enough into my past and find it. Now, normally when I give this talk, the people who are watching it are usually kind of in a Java or a C++, C# or anything other than C++. So I normally say, that's okay. You don't need to read this code. The only thing you need to take away from it is verbose and is pretty impenetrable. I know C++ can be impenetrable anyway, but I think this is particularly impenetrable. And don't even go there in terms of the Hungarian notation. That's part of my past. I'm not proud of, but we get over these things. Anyway, the point is that this test does quite a lot of stuff. Now, when I wrote it, I was quite pleased because I had managed to squeeze lots of functionality into a single test. And if you're thinking that, oh, hold on, he's chopped the name of the test off the slide, perhaps to make it fit, well, you would be wrong. One of the optimizations I made was that you don't have to write the name for a test or a description. Because, you see, I found that to be quite difficult. So I decided that if I didn't have to do it, then I could save a lot of time. That seems perfectly sensible. Yeah, I should get on with writing the code and stop faffing about with all this namby-pamby kind of like, wordy stuff. Let's just, the code, everything's self-documenting, lovely. A few months into this parser, I discovered that there was a bug in it, and so I went back to the tests, and I thought, that's great. Test-driven development, this is fantastic. I'll write a failing test. I'll go to one of the existing tests. I'll just be able to slot in the scenario, and lo and behold, fix it, and we're done. We're in and out within no time. And of course, I came to look at the tests, and then I realised that I didn't know really what any of them were actually doing, and which was the most sensible one to add this other behaviour to, because I couldn't work out what any of them were doing. As a consequence, when I did try and write a new test, I broke something else, but I couldn't really see what it was I'd broken about the other scenarios. And at that point, I realized that, I'd spent all this time optimizing for writing tests rather than kind of thinking about the readability of them and effectively what they're going to say to me in sort of, even weeks, months, kind of years, or to anybody else for that matter. So when we talk about optimization, we often talk about Tony Hoare's observation, which is premature optimization is the root of all evil. So we generally think about this in a kind of a performance kind of terms. But John Carmack, who's famous for ID software and Doom kind of Quake type stuff, made an observation that you can optimize other things prematurely as well. For instance, maintainability or flexibility, extensibility, kind of all the abilities, I guess, but also security and robustness. And therefore, in this particular case, I had optimized writing tests over reading tests. I'd made that mistake of optimization. So we need to think about, other ways that we can end up falling into this trap, other places where we think we're possibly saving ourselves some time, but actually, in the long run, maybe we aren't. So I started to look back and reflect on the sort of tests I'd written over the last few months. I began to realize that there were a number of different facets of tests which were clearly not particularly good. And so I sort of coined this phrase, weak test functions. Of course, if you're thinking that I started with the acronym worked backwards, it's a backronym, of course, you're right. It definitely helps the fact that it spells WTF. And this is probably the most referenced cartoon around that, around code quality, WTFs per second. Certainly my tests at that point, there were plenty of WTFs very well. But what's kind of, what do we consider, what effectively makes a kind of a WTF in a kind of test sense? Well, here's a kind of a list. We'll look at some of these in a kind of more practical sense a little bit later. But for the moment, these are the sort of things that I kind of noticed, both from my time back then, but also in more recent years, other things that have kind of cropped up that have made me consider what tests are particularly weak. So the first one is multiple responsibilities. Certainly, my example test there tested lots and lots of different things all at once, and that's particularly poor because when you get a failure, you don't actually know what that is. So you have nothing to do but to no recourse but to debug the test, unfortunately. So there's nothing. And I guess related to that is the second one, no clear intent. A consequence of having so many responsibilities, you don't know what scenario one particular test is focusing on, because maybe it's focusing on more than one thing. And therefore, if you do break something as a consequence, it's difficult then to work out what behaviour you may have broken as a consequence of your change, because unrelated responsibilities may well have been broken or not. You don't know. Something that crops up more recently, in particularly with mocking frameworks, is this idea is background noise. So tests end up having a considerable amount of incidental details. So mocking frameworks, you suddenly find that tests have 90% of it is code for setting up mocks left, right, and centre. But actually, the sort of the meat of the test, which is the kind of invocation of the behaviour and the arguments required to do it, and the view asserts, is just utterly lost in a kind of a sea of noise. Next is behaviours are sometimes quite difficult to test. Something where you have a simple function with inputs and outputs, that's generally you can observe look at the output and inspect the state and say whether it's good or bad. But with some code that maybe sort of calls into other components, and where you're sort of looking into components, maybe caches or things that kind of perform other stuff underneath that are perhaps not directly related to that functionality, they are often they end up getting used as a proxy for the actual behaviour that you're trying to observe. We have an example later, which is where we use logging as a which is the side effect of seeing a log message as being an example that a particular behaviour occurred. I mean, actually, all that we've really tested is the log message exists, not that anything kind of happens. So you'll see example. I hope that answers the question that has popped up around what side effect. So side effects in this sense are things that are not directly related to the operation itself. So it might be instrumentation, logging, stuff that's kind of happens off to the side. Next up, tests. And this is a really tricky one. Tests that are either overly or underly prescriptive. Brittle tests kind of like bug us all, because they're tests that you only have to breathe on the production code and they end up failing. Or the opposite, which is that you see a whole load of tests, quite excited and think there's great coverage there, and it turns out that absolutely none of them would fail, pretty much, unless you basically did something drastically wrong, like not setting up, returning null pointers everywhere, that kind of thing. So there's kind of balance between a test being able to being restrictive enough that it fails when it should fail when the production code changes, or but not sort of overly prescriptive so that it fails continually. And that's a tight balance. I have an example of that later. And then the last two are kind of related, I guess. Non-determinism shows up. The tests work fine on my machine. I push the changes to the build server, and lo and behold, all of a sudden the tests start changing, because it turns out that the build server's currently running in a VM alongside 50 other VMs of other people's build servers, and so is actually running at like a 100th of the speed of what my developer machine does. Or maybe it's being migrated across the network and therefore right in the middle of a test or something. So us kind of relying on certain aspects of things that happen in a timely fashion just basically go out the window. And then obviously what happens is people either comment out tests, or they end up trying to run the tests 10 times in the hope that at least one of them passes, that kind of thing. So clocks, that kind of thing, is a good way of determinism, or relying on particular functions like GUI generation, that kind of thing. And finally, kind of unmanaged resources. One of the differences between running in production and running tests is often that in production code we can hold on to resources for the lifetime of the process, which means that generally we can just spin them up and then kind of forget about them, and either the garbage collector will deal with them, or they'll just get shut down when the process finishes. But that doesn't work in a testing scenario, because effectively we are simulating starting the process up many times and tearing it down. So if you spin up threads and things in the background and you don't hold on to them, they are going to trigger at unwanted times and do unwanted stuff. Therefore, it's important that all resources are managed. Naturally, with database connections and stuff, we tend to bump into unmanaged resources in that sense quite quickly. But background resources, connections maybe to background servers and stuff that last for a lifetime are a common kind of wart here. Cool. So there's, as I say, we've got some practical kind of views on some of those a little bit later. But for the moment, I kind of want to take a breather and say, so that's kind of where I got to. Things weren't particularly good. I clearly needed to up my game. It wasn't about short-termism and getting stuff out the door. Really, writing tests was more about kind of looking at a longer game. Writing stuff kind of for the future, both my future self and kind of other people. So I'm going to look into some of the stuff that in the kind of intervening time that's kind of that's been in my head that helps me kind of think about what the right thing to do is, or what a better thing to do would be. Right. So this chap here, he's not famous in any way. You won't recognise who he is, although you might find he looks a little bit familiar, and that's because it's my dad. Actually, in this photo, he is the same age as me. I'm not quite sure how I have a full head of white hair at the age of 50, and yet he still has a thick mop of coloured hair. But obviously, I just didn't get that gene from him. Now, he wasn't a programmer; he was a bookkeeper. And so kind of an aspect of part of what he did was obviously to make sure that money was accounted for. So he didn't kind of generally like mistakes. He wanted to kind of track things, and often that he would do things in multiple ways, in different ways, like bookkeepers have their kind of double entry bookkeeping that helps him kind of try and find mistakes by making sure that things are kind of updated in kind of different columns. So as a child, he could help me with my maths homework, certainly. But unfortunately, being a child, I was less interested in homework. And so, to me, it was a case of I'd rather finish an answer, get on to the next one, because ultimately my goal was to get outside and play football or go and do something far more interesting than homework. But, my dad being kind of, trying to kind of help me out would try and suggest ways when I answered a question of finding a way to kind of validate whether my answer looked right. So, for instance, he had other sort of techniques. So if he had to add up a column of numbers, he'd start from the top and kind of work downwards. And then if he, to sort of check that, he would add the numbers up again. But of course, he wouldn't start from top to bottom because you introduce biases that way. So consequently, he might read from bottom to top this time, or maybe he might pick every other number. Basically, he would try and find, a simple way of just verifying kind of what happened, whether his answer was kind of correct. And other things, basically kind of even things like, are they in the right ballpark, estimates, that kind of stuff. So he had a lot to kind of teach me. And unfortunately, I didn't realise this at the time. And it wasn't until obviously a couple of decades later that I realised that, maybe he had something, there was something worth it, what he was saying, and I should kind of listen. And I think a key part of that in terms of the testing is that, we often focus on the ideas of dry and spot, so not repeating ourselves and have single points of truth and stuff. And sometimes that kind of message is so strong that we kind of forget that, testing, there is an element of redundancy in it. It's a way of us expressing the same requirement in a different way. The production code is one implementation, but maybe we can express ourselves in words, or sometimes that redundancy is we calculate the answer in our head, and that kind of goes into the test. But basically we find another way to come to arrive at the same answer and effectively kind of plug that in. So, redundancy is not always a bad thing. Sometimes it's a good thing. And yeah, I guess if my dad was around and he was a programmer, might be the kind of thing he would say. Worried that TDD will slow down your programmers? Don't. They probably need slowing down. Definitely. This was definitely a problem I had. I was so fixated with getting the code out the door, doing some testing and moving on to the next thing, rather than maybe thinking about consequences of how I represent that and how I deal with change to that code kind of going forwards. And around that time that I joined that investment bank and met with other ACCU people, this guy Michael Furze popped up again. By then, though, I was a little bit more aware of who this chap was and what, and maybe his his pedigree, I suppose. And he'd written this book, Working Effectively with Legacy Code. Now, one of the things that at the time I had tried to get into TDD, and I spent a fair amount of time reading the classic books like Kent Beck's TDD by Example, and David Astor's wrote a fantastic book called A Practical Guide to Test-Driven Development, where he even talked about test driving GUI code, which is obviously a notoriously difficult proposition. But the problem was they were all about writing tests for new code, for greenfield code. But I didn't work on greenfield code. I always worked on pretty much on legacy stuff, code that was at least a few years old at best, maybe sort of 5 even to 10 years old was kind of more likely. And so this book kind of sort of spoke to me far more, because it talked about those aspects of code which was never intended to be unit testing, never had that in mind. And so it provided a number of ideas around how to deal with that. And the idea of seams and sensing was a key part of that. Even if you don't work with C++ or Java, which are the two main kind of languages he deals with, there are still, the messages are always the important bit, this idea about characterization tests or mocking and finding other ways to get code into test so that you can make that change safely. Those kind of messages are kind of really important. So I think even to this day, it's well over 10 years old, it's still an excellent book. Something that came from the hardware community in, I think it's the late 80s, kind of early 90s, was this idea of design for testability. There was, at the time, kind of obviously CPUs, our chips basically started to get ever more complex. And so trying to test them as a black box became more difficult because of the levels of complexity. So one of the things they started to add was extra pins and chips and functionality that allowed chip manufacturers to basically see inside and inspect smaller parts of it. And so what the design for testability idea kind of validated this notion that it was okay to make changes or to change your design purely for the aid of testability. For instance, you may not need that interface, but actually if that interface allows you to get that component under test or to mock it, then going the extra distance will actually pay off in the future. So certainly for me, I felt that it kind of validated this idea that on top of whatever we do to get the design and code right for production, any extra code that's needed to allow us to test it and change it is a perfectly valid approach. One of the questions that come in: who is the author of Practical Guide to Test-Driven Development? That's a chap called David Astor's. I think it was published in about 2002. Okay, so moving on. A classic thing that kind of pops up is this idea of the testing pyramid. One of the things that we often struggle with is this: the people talk about unit tests and integration tests and system tests and end-to-end tests, and particularly unit tests is always a tricky one to because different people have different sized kind of units. One of the things I like from Kent Beck's writing is he distinguishes the difference between programmer tests and customer tests. Programmer tests are tests which we write to basically validate that the thing works the way we expect it to. But then, of course, there is the customer test, which ultimately is the acid test, if you like. Does it actually fulfill the customer's need? Does it do what they need? And that's a different kind of thing, aspect, and that comes from them. And essentially, they are kind of different degrees. And there is a balance between the speed that some of those things run. And the testing pyramid probably came out of a time when we're talking about big monolithic systems that are hard to change. End-to-end testing tended to be the order of the day. But a change in kind of attitudes in more recent times is that we've broken things down into smaller systems. So we tend to build less monolithic systems and maybe more in the kind of the sort of microservice where we have much smaller components. And as a consequence, they will often rely on technologies which are incredibly easy to use within a test. They support the ability to databases that clear their state, or maybe run entirely from in memory, meaning that there's no residual state. So a lot of the problems that come from kind of end-to-end testing in terms of speed and noise from other tests kind of disappears. And as a consequence, you can then test maybe acceptance to level test kind of through the system. You can kind of start there for the vast majority of tests because they run so fast. And then maybe if that sort of satisfies most of your cases, then maybe the number of unit tests you write might be less. You might have tricky scenarios you want to test, like running out of memory or running out of disk space, things that are particularly difficult to kind of engineer. And so you might have sort of unit tests kind of around some of those or other components. But, there's no reason why the bulk of tests isn't different. So, in a sense, I think it is a polygon. And that's about as much you can say about it. And depending on your kind of needs, don't feel that you have to kind of stick to the classic pyramid. And maybe the shape will even change as and when the system kind of changes. Tests are definitely not second-class citizens. A test code is something that needs to be nurtured, and so we should look after it. Often tests start out, we keep adding more and more tests to something, and we don't necessarily spend the time to refactor. So, for instance, the noise from incidental details that I mentioned can often be solved by pulling out all of that setup code into some well-defined kind of helper methods that are well named, and allow us to pull that out so that the test becomes clear again, because we can now read kind of what is going on. So we have to look after tests. They need refactoring. They need reorganizing. If we pull classes out, maybe they need to be moved around. And we shouldn't be afraid to take the time we need to keep those in sync, because ultimately they are something which provides us with our initial kind of confidence around on how self-out changes are. So they're hugely important in design. Questions come in that says, do I find acceptance tests run fast enough in the TDD cycle? I would say that in some cases that I've worked in, yes, where you have a very simple service, which is maybe just an HTTP service with a kind of a database kind of back end. A lot of those tests, certainly the entire test suite, can run within a minute or so, quite comfortably. It often, if you're using some kind of testing tool, sort of testing framework with an IDE that has support for it, often you can often start with the cycle by iterating just over the fixture that you're most interested in, and then as you kind of once you've kind of finished on the area that you suspect likely to be most affected, you can then go back and you can then run the entire test suite before you push your changes. This idea of a kind of a 10-minute build is a good thing to kind of benchmark to kind of try and stick to. If everyone can fit in there, then there's you remove the barriers from people just running the entire test suite before pushing the changes, and therefore there's less kind of disruption. That's not possible in kind of some cases. I've worked in some systems where legacy systems where the entire build was a couple of hours before you'd even written or run any tests. But certainly in sort of this kind of breaking down into smaller services makes it more certainly makes it possible. And a follow-up question is, have you ever deleted any tests that you talked about nurturing? Yes. I can't think of one off the top of my head, but definitely I have seen tests which I couldn't work out what they did. Therefore, I could not work out what they should do. And therefore, I decided that rather than leave them lingering because they were dangerous, I would remove them. At least when somebody else came to change it, they would come back and hopefully they would find that there is no test at all, rather than being misled. And that's kind of a better thing. Sometimes in the case of, there are cases where, and this is quite rare, where we've managed to change something about the system. So we've managed to design away certain kinds of failure. And as a consequence, obviously, those tests disappear, because if the code doesn't even compile in the first place, then you don't have to worry about writing the test for it. So that's kind of happened in a couple of times. So yes. Moving on. A perennial question: how do we test our tests? How do we know that the tests that we've written are actually are good? Okay, so good is a very subjective quality, but maybe the question is, how can I test that a particular behaviour is something which is for which we have kind of coverage for? And back during my university days in the kind of late 80s, I was introduced to this idea of mutation testing. Sadly, at the time, my head was filled with writing demos for 16-bit micros, where it was all about visual presentation and speed, and therefore this kind of ran over my head. And so I kind of treated it as a fairly pointless kind of exercise. But bizarrely enough, a couple of decades later, and I hear this term, and then I look back and realise that this is is actually quite a valid kind of idea. This idea that we've written some tests, and we'd like to know possibly what kind of scenarios have they caught things. If you're working in a kind of a TDD style where you only write production code in response to the tests, the chances are that you should have only got the minimum number of tests you require, and that hopefully those scenarios will be eked out. But if you're kind of looking at from a legacy perspective, then maybe you want to find another way to see whether those tests are working for you. Now, there are some automated mutation testing tools, and they generally rewrite code inside. So they might turn conditions back to front and make certain changes that will try and change the code in such a way that so they won't kind of set things to null so that the entire thing just blows up, because that would be pointless, but try to change subtle behaviors, which are the kinds of things a programmer might do by accident. I don't tend to use it. I don't really have much experience with automated mutation testing, but certainly manual mutation testing is something which I've often used when I start on a new code base, and I sort of want to make a change, and I want to try and see if there is any coverage around the particular thing I'm doing. Because one of the problems we often have is that not everybody sticks tests in the same place in the same way. We might not have the same structure. Somebody might package them by layer. Somebody else might package their tests by feature, and sometimes somebody doesn't know, so they might stick them into a kind of another place, or they might see their behavior as part of another class. They get refactored, and then they don't end up perhaps where they didn't get moved at the time. So mutation testing, manual mutation testing, and inserting either assert false or changing something is a good way of then running the tests and seeing actually what breaks, so you get a feel for how much perhaps the original author perhaps or the maintainers have put around that piece of code, and therefore give you an idea of perhaps how safe you are to kind of make changes and where you'd slot them in. Bonus question: how did you get that through code review? I'm not sure I understand. How did you get that? How did I get the deletion through code review? Maybe the question needs, could whoever asked the question, I'm not quite sure what that refers to in that. So I'll come back to that question in a bit. So another mistake that I kind of made when I started on test-driven development, and this because we generally start with a very simple examples. In a classic example is we write a calculator, and we write add and subtract functions, and we write tests for those. And because they tend to be very functional things, because they're very easy to write, we tend to end up with this association around methods and tests. And a kind of a knock-on effect of that is perhaps our test names then also end up using the same language that we use in our test names as our methods, which of course ties them quite tightly together. But of course, as our code gets more complex and our classes kind of develop further, we suddenly find that internally things might kind of get moved around, and therefore those behaviours might move. Or we start to ask ourselves some slightly perverse questions like, how do I test a constructor? Or more bizarrely, how do I test a destructor in C++? Or how do I test a private method? And yet, these are really kind of non-questions because that's not the level that we kind of should be testing. What we should be focusing on is a slightly higher level. We should be thinking about the behaviours that we want to exhibit from our code. For instance, I might choose to do something in the constructor. If I then decide not to do that eagerly in the constructor, but maybe I decide to do that lazily on demand in another method, no test should change as a consequence of that. I shouldn't change the test that tested the constructor to now test the method because that's wrong. Effectively, the behavior is still the behavior. Well, when I invoke the constructor and then invoke the particular method, I should expect the outcome to kind of be the same. So there should be a focus around behaviors and not methods. And a consequence of that is you'll stop naming tests potentially with methods within them and focus more on the behavior under test instead. Coming back to the question, how did you get that through code view? Appears to be deleting tests. I guess that they would have just gone through code. They would have gone through like anything else. They would have just justified that they were having no impact whatsoever, or that they were dangerous, same as any other piece of code that was bad, and that they should be removed. Maybe I was lucky enough to be working with people who would agree that there was very little value in having tests that failed, and that we would quite happily remove them rather than kind of leave them lingering around. I tend to be quite strict about that. I don't like noise within tests, within error warning levels, that kind of thing. So I guess I just tend to be strong-willed enough to have my opinion felt. They should definitely be gone. Deleting code is excellent. Deleting tests, if they serve no purpose, definitely. Of course, if there's a way of maybe as part of that review, somebody might question that there was something in there, and you may have a discussion, and they may turn around and say, well, actually, there was something in there, and we need to write a test for it, in which case maybe we'll undelete the test and we'll refactor it and come up with something else instead. But I don't remember that, certainly in the case of the things we deleted, because those. Oh. And finally, something which is maybe a little bit more recent is this idea of executable specifications. The fact that if you've ever worked with a code base where there is a huge amount of paperwork involved with describing the functional specification, and somebody says, well, how does this thing work? And what you find is you have to go and read the document, and then you need to find Annex A and then Annex B, and then probably somewhere there's a revision to a document. And so actually being able to answer what the system is supposed to do is actually impossible, not without a huge amount of tracing. And probably the documentation isn't even up to date. So all you're going to get is a stale interpretation of what that is. So one way around that is to consider, can we embody that same information within the test specification? Can we describe that functional specification within code? And that's what tests kind of allow us to do. And then we can answer the question, what does this code do? We can look at the test and says, well, this is what it does. This is what we hoped it would do. Now, that doesn't mean to say that it's not still right or wrong, because we know that actually debugging the requirements or the specification is generally where a lot of the problems is. It's often not about building the thing right, but tends to be building the wrong thing or not building the right thing. That's where the real kind of bugs are. So we can't kind of help that, although there's elements of well specified tests might kind of help you linguistically deal with some of those behaviors. Ultimately, they won't help you, but at least they will help you say that when you just make a decision of what the system should do, that going forwards, the system will continue to behave in the way you expect until you make another change. It doesn't deviate from that piece of paper or that mountain of paper, as more likely the case that's sat on somebody's shelf somewhere, or probably on a SharePoint server or something. And then very briefly, just to kind of wrap up this section, this kind of idea of strength of character came out again, coming back to that time when I was working with Phil and some other people, not in his team, but within another team. I had to make a change to a class which was buried in the middle of a service which had a huge number of dependencies. It was a monolithic in all the senses of the word. And to work on it was incredibly painful, and involved a lot of set up, a fairly beefy machine because it was massively multi-threaded. But actually the change I needed to make was to a reasonably simple class, which unfortunately had singletons and some other nasties in it. But it seemed like the perfect opportunity to do in a kind of a test-driven way if I could get the code into a unit test. And that was going to be tricky because this was C++. There was no use of forward references. There were no use of interfaces. Everything was concrete types. And so I had to make a decision. We had talked about unit testing for a long time within the team, but unfortunately, nobody had kind of taken it upon themselves to make this happen. So I decided, at the time I was quite lucky, in a sense that I had broken my ankle and I was working from home. So I managed to not be in the sight of the rest of the team, and particularly my manager. So I took it upon myself to spend a few days just trying to get one test around this particular piece of code, knowing that if I could get it under a test, I could make the change easily through unit tests, prove that it worked, and that would sort of, open the floodgates for other people to write tests. It took 3 days just to sort out headers, forward declarations and stuff to get this one test into some kind of test harness. I also had to lift out 2 singletons as well. But at the end of that 3 days, I managed to write the first test, and then I quickly managed to write a whole suite of other tests around the class. And as a consequence of that, I found 5 bugs in that one class, one of which was a leaky handle, which almost certainly was the result of instability within the system, and also some behaviors around the size of integer types, which was about to kind of bite us because we were about to deal with data that was over kind of 32 bits in size. So I managed to find a whole bunch of bugs so I could go back to my boss and say, hey, look, I've got some tests around this thing. And by the way, there are all these bugs, and one of them is probably the instability. And that felt kind of much nicer to be able to go and kind of report that. I then made the change just through unit tests. It went in, and then it went in. I did a cursory kind of test, sort of classic kind of integration and system test on my local machine to prove that it was behaving, but ultimately that took kind of minimum amount of time. It went out with no kind of issues. So yeah, sometimes we do have to make a tough decision to get that first test in place, but in this particular case, it was worth doing because then other people were brought on board with the idea, and they started to write tests themselves. Another question. Do execution time, performance, or load tests also fall under the category of tests that check behaviours? Or in other words, what do we mean by behaviours? Yes, definitely. So we have an example. There was an earlier question around side effects, and that kind of goes around logging. So I definitely think that if there is if somebody has specified that the system must return within 10 milliseconds, for sake of argument, for 99% of calls, then that is a behavior which has to be, should be validated, and we should have tests around it. Indeed, I worked on a web service where we had a constraint of 10 milliseconds, and we put some performance tests in very early on around that, and we were quite happily well within our 10 milliseconds. And then there was a change made to the logging configuration that suddenly sent us way over that into kind of like the 80 to 100 milliseconds for the majority of calls. And naturally, as we kind of looked back over the change, it didn't make sense. But I discovered that there was an issue with the log4net library, that when you used a certain type of global property, it did some stuff around threads, which was incredibly expensive. And that was the thing that caused us to suddenly go over our constraint. Now, if we hadn't had those tests in place up front, that would have been an absolute nightmare to find. So I feel quite lucky that we had performance was such a key characteristic of the system that we made the effort to do that, and I'm glad we made to do it all of us. But there are other examples as well. Anybody who is a stakeholder in the system, that could be operations, application support, those kind of people, if they have a stake in the software, then tests should be around that, because if they are relying on instrumentation, metrics, log messages, there should be tests for them. And we'll see an example of that in the section. Excuse me a second. So on to the kind of the second part, which is around what it means to kind of write good tests or write strong tests. As we know from the classic bug, as we know from the classic joke, there are two hard things in computer science, and naming is one of them. Naming is hard. It's really hard. As you'll remember back to my C++ example, I found naming tests so hard I didn't do it because I didn't like it. It was too hard, and I thought that I could just do it all in code. I didn't understand the benefit of it. In particular, this idea that that's part of slowing down, actually thinking about what is it I'm trying to convey, and can I convey it within code, is particularly difficult. So when we talk about naming tests, really we're talking about describing their behaviour. So I would say that if I can't name a test or I can't think what it is I'm trying to do, then that's probably a smell that I don't really know what I'm doing. Maybe I'm not focused enough on what it is. And a common query around this is that sometimes I just need to write some code and then kind of see what happens, and I kind of get that. But I think that is a different thing. To me, spiking or experimenting around something is a different phase of discovery around design, and that definitely kind of can go off to one side. But I think once you get to the point at which you know what you're doing and you're starting to commit production code that is suddenly going to make its way into your main branch, at that point there should be some form of test around what's going on, so that you can convey what that behavior is, and so that people know what it was you were after. So I think there is a sort of a crossover point where those test names need to go. You should be in a position where you're saying, I know what it is I'm doing. I should be able to describe what it is fairly succinctly. And maybe you won't get it right first time, and maybe it gets part of your refactoring. You will come back to that, and you will make those tests. You will maybe rename them or clarify the language, because you'll learn. Nobody kind of gets this stuff perfect first time, but at least you kind of can start somewhere, and you feel that it's kind of along the right sort of lines. The second thing is, particularly around kind of naming and stuff, is this idea of we often run tools like static analyzers over our code to find bugs, but we often run code formatters and stylistic tools like StyleCop and C# or Go format. One of the things about tests is they are a DSL for a different kind of audience. They kind of convey different things. Production code might be called, methods might be called in ad hoc orders and functions, whereas tests tend to be more about creating a narrative. So, for example, a test fixture can often be read kind of from more top to bottom, because we kind of have a beginning, a middle, and an end. So this is an example in C#. And now C# generally has Pascal case for its class names and method names, but here I've eschewed that and gone to underscores because it's impossible to read those. In fact, there was an IEEE survey, an IEEE paper that was released, I think it was in 2015, where it talked about variable name lengthening and readability. And I think that underscores, multiple word variable names with underscores are 80% easier to read than longer names. Now, that's just for short variable names. So you can imagine that for longer method names, that potentially, is quite a bit more of a saving, or at least improves readability to some degree. So here I've opted for underscores instead. And I can read it sort of from top to bottom. So I have my fixture, which describes the behavior, which is that a client will automatically reconnect. I have my arrangement or my kind of setup, given the service is already running, when the connection is lost, and then I have two kind of behaviors. Then it logs a disconnect event, then it reconnects in the background. So here I'm describing two things that happen when that event kind of disconnection kind of happens. And so you'll probably recognize that this is uses the classic Gherkin kind of given when then syntax, which is a nice way of wording things if you're kind of quite new to this, and you're looking for a way of kind of focusing on the different parts. Other test frameworks talk about arrange, act, assert. It's the same as given when then. It doesn't matter what you call those three parts. You can come up with whatever you like. But that's sometimes it's a nice way. It tends to be perhaps a little mechanical at first, but hey, the point is that if it helps you write something more meaningful, go with it. You can always kind of come back and change it later. Yeah, naturally, I wrote a C# unit testing framework just to kind of play about. And something that I wanted to see was I didn't like the kind of underscores. I wanted to see if there was a way of doing it differently. If I could just do it with have plain text, which was more like what I'd done in a C++ framework, because I had the power of the preprocessor to allow me to write a test description in natural language. And so here I've written an extension method on string called is, which is not something that I would ever probably dream of doing in production code. But in the case of tests, where I'm in a much narrower domain, and it allows me to write things without having to deal with punctuation, with apostrophes, that kind of thing. If it makes it more readable, then I'm happy to go with it. The other thing is I've kind of dropped the kind of give and when a little bit more. So we've got so the service is happily running, which is maybe a little bit more what's the word? A little bit less kind of rigid. Then the connection is lost. So it logs a disconnection event and it reconnects in the background. So there I've kind of got rid of the thens and tried to make it read a little bit more like maybe like a story. Now the order of those two things is kind of important, but it at least it kind of shows that it tends to be tries to be a little bit more narrative than rigid. Obviously, if you're using, as I mentioned in C++, you can use the preprocessor, which is much maligned for many good reasons, but potentially it has use for allowing you to write things a little bit more naturally. Similarly, if you're working in F#, you can have method names and class names that have all manner of characters in them. Again, not very easy to call that kind of thing from production code unless you've got kind of IntelliSense working for you. But again, in that sort of domain of tests, it's a good thing. So focusing a bit more on kind of specific kind of scenarios that I'd called out kind of in my list of WTFs. Here is a classic case where we are testing some input and we have a set of inputs that we've come up with. We've decided what our test cases are going to be. And so we kind of stick them in a nice little table. We add some kind of trues and false to say what they are. Bish, bash, bosh, kind of job done. But then we come back to it kind of a few weeks later, or possibly hours later, and then we sit there kind of asking ourselves, when this thing fails, probably what we'll get is expected true but was false, or expected false but was true. It's not telling us anything about the scenario or why it failed. Obviously, we could try and work that out from the code, unless, of course, it has a regular expression, in which case it might be a little bit more difficult. And then it's probably going to be even harder to change. So, I'm sort of looking at asking myself, the first one is an empty string, fairly obvious. Second one, numbers, that's okay, that makes sense. It looks like maybe there's some punctuation in the next one, but then there's also punctuation in the last one, but it doesn't like it, so maybe there's a difference. So is there a simple way we can kind of improve this? Definitely. So one nice easy way is to replace those constants in the test cases with some words, with some much longer words. So here, I now know that empty is not a valid scenario. Numbers are valid. Punctuation is allowed. That's okay. And now I know that white space is invalid. I know that it wasn't the parenthesis or the square brackets that it didn't like. It was specifically that piece of white space. This will suddenly makes this a very simple change, and it makes a so again, creating a constants for true or false is a very easy way. You can do the same thing with integer values, perhaps for for codes and error codes, that kind of stuff. Another way, if you're using an NUnit style framework, is to make use of the fact that the last parameter to assert is a string. And so here I can, instead of having to squeeze my prose into sort of some kind of identifier that stops me using punctuation, effectively I can just use a string, and then I can get back into natural language again. And then when the test fails, it will say numbers are valid, failed, or white space invalid, and we'll have an idea of what it was about that scenario that failed. The question is that's come up there: is it not better to capture that extra description in test names or auxiliary info? So that's a very good question. Now I've kept the test name in particular. I've used test cases here. I would certainly be quite happy to split out each of those into individually named test cases where that test case would be input not valid if empty, and or numbers are valid input, and where I would use the name of the test. That would definitely be definitely think that would be a good thing to do. Sometimes, though, it's a case of maybe there are good reasons why it's easier to just kind of create a table rather than create lots of. Perhaps if there's a nice refactoring tool that could turn test case into things, then maybe that would be a great kind of that'd be a great refactoring to do. A refactoring tool. If only there was somebody who worked at a company that provided good refactoring tools. Maybe consider doing that. I definitely make use of it. Hopefully that answers the question. Okay, something I mentioned in the abstract of this is this idea of a test should only contain one assert. And this is a classic bit of law, and I think there even have been attempts to create tools that try and enforce the fact that there's only one assert per test. But what was that all about? Where did that really come from? Well, it wasn't really a rule about only containing one assert, because that doesn't really make sense. But what they were trying to get at was this idea of a behavior, trying to validate a specific behavior rather than having multiple responsibilities of multiple behaviors. So therefore, it's quite possible that one assert is generally all that's needed to represent one behavior. So here is an example of a test, and coming back to the talk about other stakeholders, this is a method, a test about calculating a result, and you can see that the first assert basically checks that the value of the calculation is some particular result value. Well, that's great. That's what the user really cares about. But then there's this other behavior, and this is around log messages. So if I remove that log message, all of a sudden a test called calculates the result fails. But you'd ask yourself, well, why would removing that log message fail the calculation? But it hasn't. Really, all that's happened is a separate responsibility has failed. But we happen to have captured that in a single test. So what we need to do is break that out. Another common smell is the word and. So if a test says it does something and something else, again, that's a good sign that probably there are really two different behaviors that need splitting out. And this is me splitting it out. So one of them is about calculating the result. And then the second responsibility is about instrumenting the calculation. So now we've kind of brought out the fact that really there's a different bunch of people. Maybe there are the operations people that care about how long calculation took, and they're maybe dealing with they're taking that data, they've got to parse it somewhere, they're using some kind of log or tool to scrape that data and calculate it. And we probably care about the fact that, or they certainly care about the format of that message. Hopefully we're using structured logging rather than the kind of free text logging, but sometimes we have to make do. But the point is that is a different behavior that's aimed at a different set of stakeholders. That's not the end user that necessarily cares about that. They care about the result. But here, this is about the kind of the operations side and the monitoring side. So we've called that out as a separate behavior. So what does it look like when we do have multiple asserts? Well, here is we have an HTTP result, HTTP request, and the result type of that. Now we've chosen to use a compound type rather than throwing exceptions on error, because let's face it, the network is always a bit kind of noisy, and we should expect success is always an option, so to speak. Failure is always an option, and what we've done is represent that in a single value where we have both an option if it's a success, and we have an option holding our error state if it's an error. So when we make our test, the first thing that we need to do is to validate that. If we expect the success state to have a value, we need to check that. But if we have a successful state, then we also need to check that the error state isn't set, because it wouldn't make sense for both success and error to be set. Hopefully, the object itself will protect itself against that kind of state. But so we first of all check some preconditions, and then effectively we can then go on to say, right, okay, we know that the success value is true. We can now delve into it a little bit deeper, and maybe we can do things like check the headers, check the body content, and they would perhaps be done as separate tests. There might be one thing that says about what headers return, a separate test that checks that. We may choose to factor out those two asserts around the success value, which into a sort of a single function that maybe asserts assert the result state, and that may be handled sort of differently. That would reduce some of the noise. But ultimately, we can have multiple asserts because they are all on the same part of the same behavior. It just happens to be the type itself has multiple values that we wish to validate. I talked about overly prescriptive tests. This is one example. I worked on a system where we were using the date and timestamp within an ID. We cited out a test that basically talked about generating an ID and a unique ID. That's quite difficult to check that something returns a kind of a unique ID. So we kind of changed it to basically talk about the fact that what we do is we'd have an ID would be generated, and there were some constraints around that ID because it had to tie up with another system that we were dealing with, and so there were sort of certain constraints around format, but there was some leeway on our side. Originally, the test just basically did a hard-coded. We mocked the clock, and then we performed it, and then we did a test around a hard-coded string. But they didn't really tell us anything about the ID and aspects of it that were fixed, and perhaps those bits that were variable. So we tried to sort of loosen the start a bit by changing the test and saying, well, really what we care about, we don't necessarily care that the date is in ISO format. At this point, we don't care that it's in year, month, day. It could be in day, month, year. These are things we don't care about. At this point, all we needed to make sure was that the year, the month, and the day were contained as part of it. So as a consequence, we could now move things around within the ID whilst we were working on the system, and potentially moving around during development without having to keep kind of like breaking this test. We started kind of extending it with other attributes, and they could either come before or after the date, and then we could tie it up. But the idea was that rather than dealing with a particular fixed format, we wanted to kind of convey the fact that the aspects of the date was included in it, but we didn't necessarily care about exactly where they were at that time. Talking about kind of mocking clocks, a classic kind of around the non-determinism is having a timestamp, a date time, and you'll have a test that basically tries to compare that some time. You perform some action, and you're basically trying to compare that the timestamp has been set to the current date. This is the classic kind of thing that might work on your machine because within those two things might easily happen within the resolution of the standard clock interval, whereas you run this on a build server that's heavily loaded, and you can guarantee that this thing kind of won't work. So we need to be a little bit more clever about how we deal with this. The preferred approach is to mock the clock. Basically, if we have anything that involves dates and times, that involve us getting dates and times, we should pass in an object that implements some kind of clock interface. This is my fixed clock implement. So the iClock is the implementation that will pass around. In production code, it will be something that returns the current date and time, whereas for this particular case, it's a fixed clock, so it returns a fixed timestamp. And that now means that effectively, when I write the test, I fix the date and time. Back a bit. If you can't pass in, because passing a clock all the way down a call chain is quite painful in legacy code, one alternative is to use a static facade, which is not particularly good for running tests in parallel, but sometimes it's a good it's the best you can do in the short term to get code under until you can get that clock type passed in some way in an encapsulated object or some other means. So here I have got default implementation as date time now, and I can override that implementation. So to come back to the test, now my test implementation, I return the timestamp is my template. Now I don't care how long this test takes to run. The action .do can take 5 minutes. It can take hours. It'll probably fail the entire build by then, but ultimately it can take as long as it likes because that can't fail because we're coding against the timestamp. But also, it's clear from it that it's clear from the implementation that the timestamp comes from the current system time. So around kind of unmanaged resources and other behaviours. I mentioned that resources which are often kept for the lifetime of a process in production cause untold problems in tests. This particular example comes from a background cache that was implemented, and effectively, when the cache was started up, it spawned a background thread that was unowned, and then randomly it would call into a component that did the refresh, which is effectively was through some form of static facade. And what would happen was occasionally the tests would fail because instead of making one refresh, it might make two refreshes, or in some cases there were none, because the time it took for that thread to actually start and to trigger for the first time was longer than the sleep time somebody had added into the code. So therefore this code is incredibly brittle. In the case of a resource like this, the resource needs to be managed so that when the test starts, you need to know that there is no instance of it running. And when the test finishes in your teardown, you need to make sure that you wait or effectively join on that thread so that it's finished before you move on to the next test. This is another example of design for testability, because we are effectively adding code which we don't need for production, but we do need to allow us to write tests safely, and therefore is incredibly valuable to us from a testing perspective, if not from a product. So here I have I've captured that thread in a thing called background thread. I've used the dispose pattern because I'm using C#. And so in the tests teardown, I'll then call dispose. That will join on the thread, and then we'll kind of go around the loop again. And then the next test can start, knowing that there's not this sort of background thread that's kind of dangling around somewhere waiting to kind of trip us up. Or an alternative might be, do I really want this background behavior in my class? Maybe there's a different approach. Maybe the cache should be much simpler. Maybe I should be able to refresh it manually. I should have control over that, in which case I can test that directly. And then the refreshing behavior is then captured in a different class with a different responsibility. And maybe that's tested in a slightly different way. So now we can just test the sort of the refreshing behavior without having to muddle that up with the side effects of the cache. So maybe we design it differently. That's a different decision. Maybe we find another way to implement it. And finally, I just kind of alluded to this idea of sleeping in tests is always a nightmare. This one here is a case where we're sleeping for 5 seconds, hoping that in the background the thread will start up, it will go and make some request on a mock. We're hoping that all that happens within 5 seconds. And the reason why we've had to go up to 5 seconds is probably we started at a second, and then when it ran on the build machine, it went to 2 seconds, and it still failed occasions. We bumped it to 3 seconds, and then it was up to 5 seconds because, and then we found that 5 seconds is okay. But the problem with this is now whenever anybody runs a test suite, we now wait 5 seconds whether the test succeeds or passes, which is not good. I worked on a system where there were some tests, and I noticed that I was waiting 2.5 minutes. The test run took 2.5 minutes. And I discovered that of those 2.5 minutes, there were 5 tests that each had a sleep of 30 seconds in it. So if I could get rid of that 30-second sleep, I could reduce the tests to run in a second or so, instead of waiting this 2.5 minutes every single time. And the way to do that generally is to effectively to replace your sleep with some kind of synchronization object. So what we've done here is we have our database connection, which we're now mocking, and we have a manual reset event. And what we do is that we effectively wait for the reset event to be signaled. So what should happen is when the cache invokes the behavior on our mock connection, the mock connection will signal the event, letting us know that this particular action has occurred, and then we can kind of carry on. So here we've got to wait. Now I've got a wait of 10 seconds in here. Now, if this test succeeds, then it should take a blink of an eye. It should run incredibly quickly. So in the case when the test passes, we only wait as long as we need to wait, which is great. But in the case the test fails, we might wait 10 seconds to find out it's failed. Well, I don't think it really matters, because if this test has failed, it's going to take you longer than 10 seconds probably to investigate what it was you've just broken, like setting a breakpoint, running the test. And if it's subtle, that test sequence is arbitrary. So I don't think you can have that test time, wait time as high as you like, because it's only an issue if the test fails, and you're already doing other stuff at that point anyway. So that's okay. Question. When working with integration tests, how do we deal with the tests that fail intermittently due to timeouts, for example? Yes, that is unfortunate. I would say that it is often possible these days to generally ensure that the dependency, the things that we depend on, should be could be tested in a way, certainly at integration testing level, even using kind of containers and kind of VMs. There is a general, things should generally kind of succeed. There's a kind of that modern idea that that you can run the entire system on your laptop is a really powerful one, because often I don't have to install a copy of SQL Server to test against it, because I can just fire up a Docker container with SQL Server in it, and as long as my machine is reasonably powerful enough, I can have those dependencies all sitting there, and they will all behave in a reasonably timely fashion without that causing me a problem. I certainly shouldn't get any timeouts or whatever, because I'm putting them under stress, because I shouldn't be pushing any massive load through them. Most of those early integration tests are not performance tests. They are testing a contract. They're testing that, types convert correctly, that kind of thing. None of that should have any serious kind of performance implications. But if you need to have higher timeouts to deal with potentially working on lesser hardware, then that it may be something you kind of have to deal with. But hopefully, it should be possible to get those up, and they should be able to run, within milliseconds. Certainly, my experience with the likes of Mongo and Couchbase, tests run within milliseconds, and destroying the database for a new one took only a matter of milliseconds, even on a fairly kind of average enterprise laptop. So probably not an answer then, but I would hope that yes, if everything can be run on the local machine, then that's fine. Usually, what causes them, I guess, to fail is the fact that it's running on shared hardware with somebody else. In which case, really, the issue is the fact that you don't have an isolated testing system on which to deal with, and perhaps there is a way of dealing with that instead. Perhaps if you've got an environment that you rely on, then maybe that you need to somehow find a way to get that kind of to yourself, rather than having to have noisy neighbours causing problems. There are ways of obviously running tests multiple times. Certainly, we've had stuff where tests relies on external services where you can't deal with this, but you can maybe run a test 3 times, or you can use inconclusive. Is one status I've used for something where if a test doesn't, if the setup, find a way of setting, if I can't probe the endpoint, then the test fails with inconclusive. So the whole suite doesn't fail, but that fixture is then marked as, well, I couldn't read, the preconditions weren't met. So there's no point running the tests because it will just be noisy. As long as those tests run regularly to success, then the fact that they occasionally run inconclusive isn't a bad thing. Or, the chances of something slipping through the net is quite small. So to kind of wrap up, testing times, we live in inter testing times would be a particularly bad pun, so I won't go there. The way that we tend to work now, we're trying to work in a way where we deliver small changes incrementally. And as a consequence of that, we need to gain confidence quickly around what we're doing. And I think that testing and quality tests is a significant part of that kind of happening. Having a good test suite you can rely on, where you can change things safely because things are conveyed well, allows you to deliver things quickly, and that makes customers happy, and it makes the kind of business happy. And one of the things that I liked about Extreme Programming is this idea of principles, kind of values. XP has these 5 values which are kind of self-reinforcing. They're communication, simplicity, feedback, respect, and courage. And the idea is they kind of reinforce each other. And I think, from a testing kind of perspective, tests that are written well obviously communicate their intent. They tell you kind of what they did, why they failed, what the behaviour should be, so you've got a better chance of changing them. Simplicity, ideally they shouldn't take long to understand because they're only a matter of a couple of lines each, so they should be fairly simple to understand, meaning that you grasp things relatively quickly. Feedback, obviously tests when they fail, they give you immediate feedback that you've done something you shouldn't have done. But similarly, if they passed, then at least at a programmer level, it means that it's behaving as you expect. And at customer level, you're actually doing what the customer kind of hoped you did, which is fantastic. So part feedback. And respect, maybe a little bit more tenuous, this one, but I suspect that there is paying respect to your future maintainers. Trying to write good quality tests is showing respect for your future self and for those people that come after you to say, look, I wasn't, I understand that this is going to be far harder for you to explain than me because I'm doing it now, but I'm doing the best I can to try and convey what it is that I'm going to do. And ultimately, those four things together allow you to have the courage that you need, that fifth value, to make the change, to push that change into the real world and unleash it on your customer with the hope that it kind of solves their problem. And with that, I am done. I don't have a book. I do have some of the stuff is on my blog, and similarly, I've written a variety of articles for ACCU. Some of the stuff might be in those. That is about it. Sorry, overran the hour by quite a bit. Back to Phil, I guess, unless he's fallen asleep as well.
I'm afraid I'm still here. Thanks, Chris. That was a very strong talk. You definitely passed our test. So thanks for that. Now, those that know me know that I also do talks on testing and TDD and even classes and training on the subject. And I should definitely be stealing some of your material. So don't tell Chris, anyone. In fact, I've stolen your material before, so that's no news to you. Just going to wait a moment to see if any more questions come in, but I think you tackled them all admirably as we went. So thank you for that.